Hey everyone, and welcome to The Explainer. Today, we're diving into something absolutely fundamental, the invisible forces that govern our physical universe. We're literally going to pull back the curtain on reality itself to discover the hidden mechanics driving every single thing around us.
To get us started, I want you to look right at the screen in front of you. What do you, a distant star burning billions of light years away, and that screen actually have in common? Now, I know it sounds like a philosophical riddle, but the answer is entirely physical. You are all made of the exact same fundamental stuff, operating under the exact same microscopic rules. But to really understand those rules, we first need to establish what this stuff actually is.
Section 1. Building blocks of matter.
So the textbook definition of matter is pretty straightforward, right? But it's actually incredibly profound when you pause and think about it. Matter is anything that occupies space, so it has volume, has mass, and can be perceived by our senses. What's absolutely wild about this definition is its sheer universality. It applies to living, breathing things like us and entirely non-living things like rocks, the water you drink, and even the invisible air we're breathing right now. Basically, if it takes up physical space and has weight because of gravity, it's matter. Now, if we zoom way in, past anything our naked eyes can see, matter breaks down into three microscopic building blocks. First up, atoms. An atom is the absolute smallest particle of an element that can actually take part in a chemical reaction. You can think of it as the ultimate foundational Lego brick. Next, we have molecules. A molecule is the smallest particle that still retains the characteristics of a specific substance. Like a single H2O molecule still behaves exactly like water. And finally, ions. These are atoms, or sometimes groups of atoms, that carry a positive or negative charge simply because they've either lost or gained an electron. Everything around you, the whole shebang, is built from a combination of these tiny, invisible pieces. So, if these are the basic building blocks, how do they actually come together to form the macro world we live in every single day?
Section 2. Solids, liquids, and gases.
Look at the stark visual contrast here and how these particles pack together to create those different states. On the far left, you've got solids packed into this super tight, highly rigid structure. They can really only vibrate in their own fixed positions. It's kind of like a packed subway train during rush hour. Nobody's going anywhere. In the middle, liquid particles are a bit looser. They're in continuous motion, slipping and sliding past one another like a crowd flowing through a concert. And on the right, gases. Complete scattered chaos. The particles are extremely far apart, zipping around rapidly in completely random directions. It's a great visual, but it does leave us wondering, why exactly do they behave this way?
Section 3. The kinetic molecular theory. To really understand why particles arrange themselves so differently, we have to look under the hood at the invisible engine driving the whole thing, the kinetic molecular theory. First up is interparticle space. Now, even in the hardest diamond or a solid block of iron, matter isn't completely solid all the way down. There is always, without exception, physical space between the atoms or molecules, and the size of that tiny gap, it changes everything.
Next, we have interparticle attraction. Imagine this as a continuous microscopic tug-of-war. All particles naturally attract each other, but the strength of that pull depends entirely on the distance between them. When particles are packed closely together, that attractive force is at its absolute maximum. But push them far apart, and the force becomes incredibly weak.
And then comes the real catalyst, kinetic energy. Because particles of matter are in continuous motion, they inherently possess kinetic energy. Now here's the secret to accelerating the whole system: heat. Applying heat increases this energy. If you heat matter up, you're basically giving the particles an energy drink. They move faster, bounce harder, and zip around way more randomly.
So when you put those three microscopic rules together, the macro world makes total sense. In a solid, you've got minimum space, maximum attraction, and the least amount of kinetic energy. The particles are literally locked into place by their own mutual attraction. But jump over to the gases: maximum space, negligible attraction, and very large kinetic energy. The particles have so much energy they've completely broken free of each other and are just bouncing off the walls. Liquids sit right there in the sweet spot. Slightly more space, a bit less attraction, and a large amount of energy. It is a perfect balancing act. Okay, so if adding heat gives particles kinetic energy and makes them go crazy, what exactly happens when they hit a threshold, like the boiling point?
Section 4. Inner conversion. Changing states.
As you can see, changes in temperature and pressure literally force matter to shapeshift. Just following the arrows, it's clear how solid ice undergoes melting into liquid water and then vaporization into steam. And the cool part, it works entirely in reverse too. You can liquefy steam back into water and solidify it back into ice just by cooling it down. The matter itself isn't changing its core identity. It is still H2O, but its physical state is completely transformed based on exactly how much energy it has.
Let's actually walk through the microscopic mechanics of what happens when you heat a solid until it melts. It's like this beautifully logical chain reaction. Step 1, heat energy is supplied to the solid. Step 2, the kinetic energy of the particles instantly spikes. Step 3, because they're vibrating with all this new energy, the inner particle space increases. They're literally elbowing each other out of the way. Step 4, because that space increases, the force of attraction holding them together naturally drops. And finally, step 5, at the melting point, the particles just break free from their rigid structure entirely. The solid melts into a liquid. You're mechanically overcoming attraction with sheer kinetic energy.
But chemistry always has these fascinating exceptions, like sublimation. Sometimes when a solid changes state, it bypasses the liquid phase entirely and goes straight to a gas. Think of dry ice at a Halloween party. This happens with sublimatable solids like your everyday mothballs, which are made of naphthalene or ammonium chloride. Their interparticle attraction is so incredibly weak right out of the gate that when you apply heat, the molecules just instantly break free and escape directly from the surface of the solid into a vapor. No liquid phase required. Now, with all this chaotic, shape-shifting, melting, vaporizing, and sublimating going on, what happens to the actual physical mass of these substances? Does matter ever just disappear into nothingness?
Section 5. Law of Conservation of Mass. To answer that, we have to go all the way back to 1789 with pioneering chemist Antoine Lavoisier. He laid down this groundbreaking rule. Whenever a chemical change takes place, the total mass of the reacting substances is exactly equal to the total mass of the products. Think about how profound that actually is. Despite all these chaotic transformations, mass is perfectly and precisely preserved. There's a brilliant demonstration of this called Landault's H-shaped tube experiment. So Landault introduces a solution of sodium chloride into one limb of this custom glass tube and silver nitrate into the other. He carefully seals the whole thing up and weighs it. Then he literally just shakes it up, mixing the chemicals. A reaction happens right before his eyes. A dense white precipitate forms. Brand new chemical products are created. But here's the kicker. When he weighed the sealed tube again after the reaction, the total weight had not changed by a single microgram. The mass of the reactants was exactly equal to the mass of the newly formed products. So here is the ultimate takeaway for our explainer today. Matter is neither created nor destroyed during a chemical reaction, it only changes from one form to another. The universe we live in is this remarkably efficient, completely closed system of infinitely recycled, shape-shifting particles. Literally nothing is ever truly lost. It just takes on a new arrangement.
Which leads us to a final, kind of mind-bending question to wrap up our session. If matter is never created or destroyed, if it just moves, mixes, and changes state based on heat and attraction, whose atoms are you borrowing today? I mean, you could literally be breathing in an atom of oxygen that was once exhaled by a T-Rex, or drinking a water molecule that Julius Caesar spilled 2,000 years ago. Every single atom in your body, in the screen you're looking at, and in those distant stars has been around since the dawn of the universe, just endlessly recycling through solids, liquids, and gases. Pretty crazy to think about, right? I really hope this structured look at the invisible engine of matter has given you a whole new perspective on reality. Thanks so much for joining me on this explainer. Keep wondering, and I'll see you next time.